speaker is Diva Hidari, who will be speaking on winning strategies for the region Unknotting game.
Okay, amazing. Good morning, everyone. My name is Diva. I'm an undergraduate student at the University of Toronto, and as Alice said, I'm going to be discussing winning strategies for the region Unknotting game. The region Unknotting game is a game from knot theory that is played on the two-dimensional diagrams of knots from three-dimensional space that we basically project down onto the plane. And it's attributed to a collection of authors: Brown, Cabrera, Evans, Gibbs, Henrik, and Kreinbell. You can find the prevalent paper at this JSTOR address. This is an expository talk, just to be clear. So I'm going to be discussing some readings from works of theirs that I think are interesting. Okay, so before I get into explaining what the region Unknotting game is, I need to provide some mathematical background from knot theory. And the first important thing to realize is that when we have a string and we knot it up in some way, we can always untie the knot. So if you've ever left your headphones in your backpack and it's gotten a disgusting mess of tangles, even though it looks really bad, you can always just look at whatever moves and crossings and sequences you took to get to that point and undo those exact moves and unravel your knot. So because of this, these kinds of knots that are on strings almost, aren't very interesting to us mathematically. So mathematical knots, rather, are loops. And to demonstrate this, if you think about the simple overhand knot that we're all familiar with, this is obviously a very easy knot to untie, but as soon as you join the ends of this knot together and form a loop, then what we end up with is the trefoil knot that I think some of you guys might be familiar with, which is the unique knot with 3 crossings. So when we talk about knots in mathematics, that's what we're talking about. We're talking about these closed loops. Okay, so there are certain moves that we can perform on knots that allow us to change their structure. And in particular, I want to talk about 3 important moves that we have. The first is a crossing change. This is exactly what it sounds like. So if you have 2 strands, and one of them is going over and one of them is going under, all the crossing change does is it switches the strand that is on top. So previously this strand was underneath, now we make it the top strand. The second move that we have is what we call the region crossing change. So if you look at the diagram of a knot, so for example, let me draw a little trefoil knot here, you'll notice that it creates these regions in the space of the plane. And what the region crossing change says is pick a region and switch, perform a crossing sign on all of the crossings that border that region. So for example, if we selected this region here and we performed the region crossing change, then we would get a knot that looked something like this. There we go. So basically we've just switched the strand that was on top in this crossing and likewise for this crossing. So that's the region crossing change. And the final kind of category of moves that we want to look at when it comes to dealing with knots are right master moves or read master moves. And in particular for this talk, we're going to focus on R1 and R2 moves. These are moves that actually preserve knot structure. So the R1 move is just untwisting a loop. What it says is that if you have a piece of your knot that looks like this, we apply an R1 move and we can just make it look like this. And just to show that here, really straightforward, this is what it looks like before the R1 move, and the R1 move says untwist that portion. And the R2 move just involves sliding pieces of string over one another. So the R2 move says that if you have something that looks like this, where this strand is over top, we can slide them away from one another and get something that looks like this. So for example, we have 2 pieces, one of them is on top, we can just pull them apart. And for those of you guys who have taken an algebraic topology course, a lot of these rules for manipulating knots are very consistent with the rules you have in topology. No cutting, no tearing. We can make these moves where we pull and slide things apart, but we can't, cut a portion of the knot and unravel it and retie it or anything like that. Okay, so importantly, number 1 and 2, the crossing change and the region crossing changes, change the knot structure. They can turn a knot into a different one. But move number 3, the read master moves preserve knot structure. Okay, here's the first key takeaway, which is that crossing changes and region crossing changes can undo all knots. So if I'm given a knot, even if it's like some sort of like horrible, disgusting diagram with a bunch of crossings, I can always untie it using just crossing changes, just by switching the signs of certain crossings, or just using region of crossing changes, or some combination of the two if you're so inclined. So that's kind of the first key piece of information that's needed here. There are a couple more things that I need to go over though before I can introduce the region unknotting game. And the next big thing I want to talk about has to do with orientation. So when we have a knot, the first step to picking an orientation is picking a starting point for us to travel around the knot. Doesn't matter where it is, let's just say I pick it to be here. All the orientation is picking a direction of traversal. So let's say we pick this direction. That means that when we consider this knot, we go around in this manner, like this, all the way around. So for example, we reach this crossing first, that's crossing number 1. We reach this crossing second, number 2. If we had chosen to go around the other way, this would have been crossing number 1. I think you guys kind of get the gist. So the orientation might seem like kind of a useless construct. In reality, we introduce it because it allows us to discuss the sign of a certain crossing. So a knot can actually be entirely determined by this property, by the signs of its crossings. And we have a convention here that helps us out. So if we're looking at 2 strands on a knot that have been oriented, what we do is we look at the direction that they're going when they cross one another and match them up to a couple of predefined orientations or predefined signs. So if the strand that is over top is going up and to the right, kind of like in the direction that we read in English, and the strand underneath is going up and to the left, this is a positive crossing. On the other hand, if our overhand strand is going up and to the left, kind of opposite the direction that we naturally read in English, this is going to be a negative crossing. Okay, so the other important thing to think about though is sometimes we have like portions of knots that can be, not exactly rotated the same way as these 2 diagrams. So in these diagrams, both of our strands are pointing upwards. But if we even just come to this first crossing here, we've got strands pointing downwards. The way that we deal with this is we basically just note that we have equivalent crossings for strands that point downwards. So if I take this exact positive crossing and I rotate it 180 degrees, I get a strand on top that goes down and to the left, and the underneath strand goes down and to the right. And because just rotating a knot doesn't change the knot structure, it's an invariant, like knots are invariant under rotation. Rotation here won't change whether the sign of the knot is positive or negative. So this is also a positive crossing, and we can do the exact same thing here, and this will also be a negative crossing. So using this then, we can kind of see, okay, this one, the strand is coming down, the strand over top is going towards the right, so this is going to be a negative crossing. Okay, so this is how we assign signs to knot crossings that allow us to determine, sorry, let me take this off, that allow us to determine a particular knot type. Okay, the final thing I need to tell you about is how you actually undo knots. So an unknot, or a knot that's been undone, is just a circle. If I can show that my knot is the same as a circle, then my knot is what we call an unknot. So, for example, if I have, here we go, so if I have some sort of knot that looks like this, that's perhaps been twisted and brought around like this, I can very clearly, using R1 and R2 moves, just untwist this back to the original unknot. I can't always do that. So for example, with the trefoil knot that we looked at before, there's no way for me without cutting or tearing to bring this back to the unknot. Like I mentioned before, crossing changes can help us untie knots. And to demonstrate that, I have another trefoil knot here. But this time, if we look at this crossing, and we switch the strand that is on top and the strand that is on the bottom, what that allows us to do is pull this piece outward, and we're back to the unknot. Okay, so that's how we say a knot has been untied. If we can use any of these, knot preserving moves that don't cut or tear the knot, to bring it back to the unknot. Okay, now let's talk about the game itself. The region unknotting game is a two-player game that is played on what we call an alternating twist diagram. So alternating twist diagrams have two key parts to them. The first is the clasp part, and the second is the twist part. So in terms of the clasp, I'm going to draw one, and then I'll point out on the diagram the different parts of the knot. So, okay, so this is the twist part. It's this part down here where the strands of the knots have been kind of twisted around one another. And this is the clasp part. It's this part of the knot where two loops come in together to form a clasp of sorts at the top. So we've got two loops here. Sorry, let me get a better one. There we go. We've got two loops here that are making a clasp. So twist part, clasp part. That's what these alternating twist diagrams look like. This is one that has 4 crossings. So 1, 2, 3, 4 crossing alternating twist diagram. And when we want to add on crossings, all we do is we add twists at the bottom. So instead, if I had wanted a 5 crossing knot, I would have drawn something like this. So we've added an extra twist at the bottom here, and now we have a 5 crossing knot. Okay, amazing. So now let's talk about what the region unknotting game actually is. The game involves 2 players, and one of them is called the knotter, and one of them is called the unknotter. Each turn, one of them will pick a region of the game, and they can decide whether they want to perform a region crossing change on that region or not. So, for example, if I were to select this region up here, I can make a decision if I wanted to switch both of these crossings, or if I wanted to leave them as is. And once a player has selected a region, that region is removed from the gameplay. No one else can touch it for the rest of the game. The game ends when all the regions have been played on, and the way that you decide the winner is by looking at the final knots diagram after all of the region crossing changes and seeing if it is equivalent to a non-trivial knot or equivalent to the unknot. If it's been unknotted, if the diagram is equivalent to the unknots, then the unknotter wins. If it is a non-trivial knot, then the knotter wins. Okay, so those are the rules of the game. And obviously the big question is, if we play the region unknotting game on an alternating twist diagram, who has a winning strategy? And the first thing I want to talk about is kind of some investigation that was done into smaller cases of this problem. So in particular, there were proofs devised for the case of 3 crossings and 4 crossings. In the 3 crossing case, it was shown that the unknotter always has a winning strategy. And in the 4 crossing case, it was shown that the second player always has a winning strategy. And I'm not going to go through these proofs, but they do give us some key ideas for how to prove the general case, which I will do. So the proofs leverage a couple of facts. So the first is the uniqueness of knots. If I have a trefoil knot, like I said before, that is the unique knot with 3 crossings. And previously, I drew it like this. There we go, something like that. But if we want to find an alternating twist diagram with 3 crossings, then what we actually draw is something like this. And these are the same knot, right? There is a series of R1 or R2 moves that I can rearrange the strands without cutting or tearing and get me a knot that looks like this. And because the trefoil knot is the only knot that has 3 crossings, and knots are entirely determined by all of the signs of their crossings, we know that if at the end of our game we have a knot diagram that doesn't match the sign configuration of the trefoil knot, then the unknotter has won. So in particular here, all of these are negative crossings. So we have 3 negative crossings. And in general, trefoil knots have 3 crossings of the same sign. So a trefoil knot will either have 3 positive crossings or 3 negative crossings. So if at the end of our game we happen to have some situation, for example, if I change this crossing, where this is now a positive crossing, this has to be equivalent to the unknot, because we don't have any other configuration of signs that will give us a knot with 3 crossings. And the same thing applies for 4 crossings. So the figure 8 knot also is a unique knot with 4 crossings. Yeah, I can take a question.
When there's no arrows in the picture, how do you decide like
Oh.
what's the sign?
Yeah, awesome. Okay, this is a great question. So I guess the first kind of answer to this is I'm being a little lazy. In my head, this knot is kind of oriented like this,
Okay.
and that's what gives us the negative crossings. But if you had actually oriented the knot the other way and gone this way, that would have given you 3 positive crossings. The point is that they're all just the same sign. Yeah, thank you for that question. Okay, so that's the first thing that these proofs leverage. And the second thing that they leverage is the existence of the clasp, and the fact that the clasp, if it's undone, can undo the entire knot. So if we look at this clasp portion here, right now these are kind of stuck together. If this clasp were to be undone, so if we were to bring one strand over the other here, there we go, and it looks like this, it's very easy for me to just unfold and untwist, these twists at the bottom and get back to the unknot. So if you undo the clasp, then you can win the game. If you undo this part, it kind of unfolds on itself. Another example that might be easier to see is here. If I just had these 2 clasps, I can undo it and untwist. So the clasp can always be used to undo the game, to win the game for the unknotter, to untie the knot. Okay, so at this point, we're ready to kind of state and prove our key theorem here, which is that if the region unknotting game is played on an alternating twist knot with even crossing number, so an even number of crossings, then the second player always has a winning strategy. And to help us go through this proof, I'm going to just start by drawing a very big diagram of an alternating twist knot. There are 2 cases. The first is when the unknotter plays second, which is kind of our easier case, and the second is when the knotter is the second player. So let me draw a nice big alternating twist knot over here. Okay, amazing. So we've got the clasp up here, we've got our twists, and we've got some arbitrary number of twists as long as we've got an even number of crossings. So it's helpful to provide some labels here, and we're going to just label very naturally. We'll say this is regions 1, 2, 3, just kind of across. Region 4 is the middle here, and region 5 is actually the outside, so we count this outer region. Then in terms of these ones down here, we've got region 6, and then yada, 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 all the way up to region n plus 2, where n is the number of crossings on the diagram. Secondly, we can label the crossings themselves. So we'll say this is the A crossing, this is the B crossing, and we've got C1, C2, all the way up to Cn minus 3, Cn minus 2. Okay, so this is our nice labeled diagram. And when we think about the unknotter playing second, since we have an even number of regions here, the unknotter playing second means that the unknotter also plays last. And because of that, we can force the knotter to make a move that is very desirable to us. The important thing to realize is that when we want to undo the clasp, what we actually need is for A and B to have opposite signs. So when A and B have the same signs is when the clasp is clasped, and when they have opposite signs is when they can be undone. So as the unknotter, that's our strategy. Make sure A and B have opposite signs. If you look at all of the regions that touch A and B, we've got 1, 2, 3, 4, and 5. None of these down here are going to affect the AB crossing. Regions 1, 2, and 3 are not helpful to us because they change both A and B. So if we had both A and B were positive originally, and we perform a region crossing change on region 2, then they both become negative, and it doesn't help us with this situation where we need them to have opposite signs. So working in any of the 1, 2, or 3 regions is not helpful to us. Yep, that's okay. The only region that is helpful to us is regions 4 and 5, because they only touch one of the knots in this crossing. In particular, region 4 only touches crossing B, region 5 only touches crossing A. Because we get to play last, we can force the knotter to make the first move on either one of these regions. And once these regions have been played on and they're eliminated from gameplay, no one else can change the relative difference of signs A and B. So suppose the knotter plays on 4 and makes B positive. All we need to do is make the corresponding move on region 5 that would make A negative, whether that's keeping A or switching it. Like I said, because the unknotter plays second, we can always force the knotter to make this move first. So the unknotter always has a winning strategy because they can undo the clasp. Okay, so the slightly trickier case has to do with when the knotter plays second. So exactly like before, you have the advantage of being able to control the clasp. So for the exact same reason, the knotter, when they play second, they get to play last. They can make the unknotter play first on one of the regions 4 and 5. So they can make sure the clasp stays closed. But there's actually one other way to untie the knot. So if I've got a knot here, where the clasp is very much clasped, but all of my twists have been undone, then I can actually just fold this part up and undo the knot. What does it mean for your twists to be undone? For the sake of time, I'll be a little brief here. I understand if you guys have questions. It means that the sum of the signs of the twist portion is equal to 0. Right now, all of these actually have the same sign. And if we just zone in on, one portion of the twist here, what you might notice is that if we change one of these, let's say we make this one a positive crossing, so now they both have opposite signs. This, with an R2 move, can just be undone to look like this. So if we make our configuration of signs, positive, negative, blah, 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 all the way down, then we can just pull our twist right apart because we'll effectively just have one strand that's laying on top. So the only other strategy left for the unknotter here is to make the sum of these signs equal to 0. Also, by my timer, I have 7 minutes left.
We have 25 minutes.
Oh, sorry, I thought I was timing for 30 minutes. Okay, that's okay. So what are we looking at here? We know that we are going to have an even sum of signs. This is just because we have an even number of crossings. So we've got 2k crossings times either some number of negative crossings or some number of positive crossings. And that is going to be equal to, let's call it W, our sum of signs down here. We have a 2k up front, it's always going to be even. And what that means in particular, I'll come back over here. So what that means in particular is that either W is equal to 0 mod 4 or W is equal to 2 mod 4. And as the knotter, if we want to avoid that case where the sum of the signs is 0, we want to make sure that W is equal to 2 mod 4. If W is equal to 0 mod 4, then we could have a sum of signs in the twist that are equal to 0. So the way that we go about doing this is noticing that regions 1 and 3 are the only regions that change exactly one of the twists in this twist portion. Any of these regions will change 2 twists. Regions 4 and 5 will just change all the twists. And because of that, regions 1 and 3 are actually the only ones that can affect whether our sum of signs is 0 mod 4 or 2 mod 4. And again, because we have the luxury of playing last, we can force the unknotter to make the first move in region 1 or region 3. Whatever move we make, we can make the corresponding move exactly like with the 4-5 regions to change the modularity of the sum of the signs back to 2 mod 4. So the knotter also has a winning strategy. Some open questions involve what the game looks like when played on an odd number of crossings. Like I mentioned before, the case for 3 crossings has been resolved, but actually for 5 crossings or anything greater, we don't know anything yet. All right, thank you very much for coming to my talk. Yes.
All right, so we have time for a couple questions from the audience.
Yeah.
Sorry, I missed the beginning. So is that the journal reference?
Yes. So this was an expository talk, 100%. I refined the proofs, I provided visuals, I made a bunch of hyperlink notes, but 100%. I listed the authors and stuff at the start. If you even want to take, I have like a paper reference.
I'll look it up.
Yeah, no worries. They go into a lot of other stuff too. In the paper, they talk about like playing knotting games on toruses. So I think it's really cool stuff. Yeah, definitely check it out. Yes. Yeah.
So you said that every knot is characterized by like the signs.
Mm-hmm.
So if I give you a number of crossing and a list of signs, like how can we say, oh, these two are different than, I don't know exactly how do we characterize a knot?
Yeah. So okay, let me.
Is it too?
No, that's totally fine. So I don't know the exact, numbers off the top of my head, but I know that there is one unique knot with 3 crossings, there's one unique knot with 4 crossings, there's 2 unique knots with 5 crossings. So for example, if we have 5 crossings, we have either a knot that has all the same signs. So if you gave me a 5 crossing knot that had all of the same signs, I would know that that was a knot. Or we have a knot that has 3 positive, 2 negative, or vice versa, 3 negative, 2 positive. And I actually think this is the star knot. So if you've ever seen, it's like a nice little star-shaped pentagram little knot, I can find a picture if we want. And if you give me any other knot that isn't one of these 2 configurations, so if you say, I have a 5 crossing knot with, 4 positive, 1 negative crossing, I know, since these are the only 2 possible configurations for 5 crossings, that this has to, in some way, be equivalent to the unknot. So it's just that, people have studied knots. They found for each number of crossings the unique configurations of the signs that will give us knots versus give us unknots. And from that, I don't have a big list in front of me, but yes, I guess if you gave me 8 crossings and 3 positive, 6 negative, that equals 9.
Do you know if we know, I give you a list, and do we, can we say oh, this one is equivalent to the unknot?
Yes, yes. So if it isn't one of the configurations that we know that gives us a knot, it is equivalent to the unknot.
Okay.
Yes, it has to be, yeah. So this one here with the 4 positive, 1 negative, that's the unknot. Same with 1 positive, 4 negative, that would be the unknot.
Yeah.